on power. This is the last topic in your unit that took a look at work, kinetic energy, potential energy, conservation of energy, and of course, this last section as well. We're finishing up chapter 5, covering pages 175 through 177. When we talk about power, the one thing we want to know is power is how quickly work is going to be done. And when you see the equation, you'll know exactly why. We can be lifting two objects that have the exact same mass, but depending on the speed at which that object is moving, that will determine exactly how much power is required or how much power is actually being used. We're going to see that power equals work divided by time. These two units we've actually seen before, so it's nice to put those concepts together. Now, of course, there's going to be a historian. We're coming to the point in our semester where we have a lot of dead people to talk about. These are the people that actually frame physics as we know it. For example, we will learn that power is measured in watts. And this is our inventor, James Watt, who was credited with the units. So a lot of your units are going to be the last name of those scientists that were given credit for them. He invented the steam engine and also worked through the facts, once again, that power equals work divided by a change in time. This is measured in a joule second. Since work is measured in joules, time is measured in seconds. You're going to learn that 1 watt of power is equal to 1 joule second. Now, when it comes to watts, we always think of electricity, what runs through your house, what runs in your school, and also what runs in your car from time to time. It's that transfer of energy when we're going from mechanical to any type of non-mechanical energy as well. We're going to learn that the energy that's used in your home is measured in watts, but more specifically, it's in kilowatts. So if you have a chance to take a look at that TXU bill, you'll notice that each month they're keeping a tally of how much power or how many units are being used in your home. There's also a good calculation that a lot of our electric companies use based on the number of people that live with you that help them to determine how much energy you're likely to use as well. And this is where your average billing comes from. So your electric bill is measured in kilowatts per hour. So in the course of that 60 minutes, how much energy or how many watts or kilowatts that you use. 1 kilowatt is equal to 1,000 watts. So whether we're talking about a kilometer, a kilogram, kilo, the prefix always stands for 1,000. Now, we're going to compare these two. We just said that power is equal to work divided by time. You've also learned the equation for work. Work is equal to force times distance. What I want you to put in your mind is, how do we combine these two? I can replace the W here with force times distance. That looks a little familiar. If you go back to the first semester, we had an equation that gave us distance over time and even displacements over time. So distance over time is another way for you to also use velocity. So go back. Power is equal to work divided by time. Work was equal to force times distance. We can take this equation and make it a part of our power equation, and power would then be equal to force times distance divided by time. If I look here, distance over time is, of course, your velocity, and that's where the substitute comes from. Depending on what information they provide you in a problem, take a second, look at your units and the steps in your guess method, and that will help you figure out what version of the equation is best to use. Now, the other thing about work and the other thing about power, you have to keep up with your units. So you always want to put in the back of your mind, anything that is energy, whether it's work, kinetic energy, potential energy, or mechanical energy, are always measured in joules, which we represent with the capital J. Power is measured in watts, and normally we would use a capital W. The reason why you will notice that I usually write it out is because if I put capital W, many of us are going to think of work. Now, if we're talking about a kilowatt, we have a lowercase k with a capital W. Right off the bat, you'll think of kilowatts, all right? Let's do an example. A spacecraft's engine does 1.4 times 10 to the 13th joules of work in 8.5 minutes. What is the power output of these engines? So, let's take a look. We are going to use our guess method, and they've given us a nice little base to start from. So, my given information, I have engines that do 1.4 times 10 to the 13th joules of power, of work. Anything that's measured in joules will either be work or energy. And it takes a time of 8.5 minutes. There are a number of us that are not happy about conversions. And this is one of those sections where converting time will be a big one. So keep in mind that whenever you see hours or minutes, our standard unit for time is, of course, seconds. Let's go for our unknowns. It says all the information they provided us with. What is the power output? So we're looking for power. And the equation that we've learned, I think we can definitely use our basic one. A power equals work divided by time. Now, substitution step is going to be used this time. Because if you look here, we're going to switch our minutes into seconds. So for our substitution step, we start with 8.5 minutes. And we already know that for every 1 minute, we should have 60 seconds. Minutes on top, minutes on bottom. These are going to cross out. And of course, from here, if you grab your calculator, we'll say 8.5 times 60. And that will give us 510 seconds. We're now ready to go into our solve step. Needed that. Power is going to equal work divided by time. Our work is our 1.4 times 10 to the 13th. And our time, don't forget to use your updated time of 510 seconds. Now, this is one of those areas where placing it into the calculator can be tricky. Go ahead and enter your 1.4 times 10, and there's a nice little arrow that looks like this on your calculator that we can use for your exponent. We're going to take that number and divide it by 510, which gives me 2.74 times 10 to the 10th power. And power is measured in watts. So, they gave us work that was measured in joules. They provided us time in minutes, and they wanted us to figure out the power output of the engine on your spacecraft. We used our basic equation of power equals work divided by time. There was a need for us to substitute, so we wanted to change our minutes to seconds. We started with 8.5 minutes, and we know that 1 minute has or contains 60 seconds. You want to make sure that whatever unit you're getting rid of, one is on the top and one will be on the bottom. That way they're able to cancel out. It left us with seconds, which gave us 510 seconds. We then wanted to divide 1.4 times 10 to the 13th by 510. If you pay attention to your exponent, you will notice that my denominator has 3 numbers, so my exponent will likely change by 3, and it did. We found our final power output is 2.74 times 10 to the 10th power. I tell my students all the time that from this point moving forward, our numbers will either be very large or extremely small. Scientific notation is something you will have to become comfortable with. Whether you are putting that number into the calculator or you're adding 2 different variables together or even multiplying. So take your time, use your parentheses, and don't hesitate to go back and check on your work. Once we go through our guess method, all of your units should match. Always go back to your problem to ensure that what you found was your unknown and also a part of what's normally at the end of that question. Now, you guys have heard the term horsepower. Horsepower is one of those things that came about based on where our country was at the time. So, if we go back, we haven't always had cars, we haven't always had highways and street lights even. Long time ago, the easiest way for us to get around was through the use of the horse and buggy. So, when Mr. Watt came up with this idea, he needed a way to compare it, to let people know how much stronger one item was over another. And the number one thing that people were familiar with was, of course, how much work a horse could do. And that's where our conversation or the idea of how horsepower came from, which horsepower is equal to 745.5 watts. Now, we still use this for motorcycles, lawnmowers, or even cars. So horsepower is huge. You hear it in racing as well. And now we know exactly where it comes from. There are always forces involved, and we'll talk a little bit more about this as we move through the unit, especially in class. We can either have an input force, and the good thing is it tells you exactly what it is. This is a force that is applied to a machine. We can also have what you call an output force, and this is the force that is applied by a machine. And there are a couple of examples that will come up preceding this video as well. The last thing we're going to talk about is efficiency. Efficiency is how well are you doing something? How good are you at doing that job with the least amount of material? The more efficient a car is, the less gas you burn, the fewer tires you have to buy, the fewer parts you end up replacing, because that car or that system has learned to operate at its highest level. That keeps your costs down, and of course, the workload of the machine stays high. When it comes to your efficiency, we'll learn in our roller coaster lab that this will be our percentage. So your work output divided by your work input. And then, of course, we'll multiply that by 100. And we'll take a deeper look at that equation in class as well. Before you go, if you have any questions, be sure to bring those to class or email them to me so that you don't forget. I've also included a link for another video that does a great job at introducing the concept of power. Every video we have is simply an introduction. It's a way for you to hear the terms. And today, we heard the terms power and watts. We reminded ourselves that energy is always measured in joules, whether it is work, kinetic energy, potential energy, or mechanical energy. We saw the way in which power and work equations can be melted into one another. So we go from power equals work divided by time to power equals force times velocity. If you need anything, please let me know, and I'll see you guys in class.